Thank you. Good morning, everyone. I'm Donato Morresi. I'm a postdoc at the SLU di Numero, and I work with the satellite time series mainly for the detection of disturbances. So today I will present a framework I was working on in the past months for mapping non-standard replacing disturbances. So I'm improving a methodology I already worked on and published in 2024. And this work is in collaboration with a statistician based in the UK, who originally developed the methodology, and then I adapted this methodology for time series analysis from satellites. So some ecological background, what are non-standard replacing disturbances? Are those events that cause the low to moderate severity, so they don't remove all the trees in a stand, and they're usually caused by drought, insect outbreaks, pathogens, also low intensity wind throws, and surface fires. And in disturbance ecology, they are usually defined and divided into pulse and press disturbances. Let's say they differ in terms of abruptness, that is the ratio between the magnitude and the duration of the disturbance. So when we have a pulse disturbance, we have a high magnitude within and a short duration, while with the press disturbances, we have a long duration but a low magnitude. So for instance, we can think about defoliator insects or pathogens that are causing tree dieback over a long time, in spanning several years. While for a wind throw or a surface fire, we can think of those events like pulse disturbances. But the interest around non-standard replacing events is related to their widespread, especially in with the climate change, and as they are closely related to extreme drought events, these disturbances are becoming more and more common, and they usually occur at broad spatial scales. So for moving to the remote sensing background, for detection of non-standard replacing disturbances, several algorithms have been developed throughout the years, starting with the Landsat time series, and nowadays with Sentinel-2 time series. And many of these algorithms are based on the modelization of phenological or seasonal patterns. So they basically use data from the beginning of the time series to model, to develop, to estimate coefficients for harmonic models. And then they provide estimates in the subsequent years, and they detect when there are deviations from the expected values. So there are several of these algorithms that have been developed either in the US or in Europe, and they are based on either on the spectral bands or regional spectral bands of the satellites or on the vegetation indices. But limitations that pose these algorithms are mainly related to the data availability that is required for the estimation of the coefficients of these harmonic models. In particular, the irregularity in the data availability throughout the year is a fundamental requirement for these models to be properly estimated. And also, they are insensitive to changes in seasonality throughout the years. So let's say they are not well suited in areas to be used in areas where, for instance, Northern Europe, where we don't have, or let's say Scandinavia, where we have many months with snow cover and persistent cloud cover. So very, very few clear sky observations are available from optical satellites. Also, these models struggle with the detection of consecutive disturbances, those that occur in a close sequence, let's say 1 year apart each other. And some of them also require the observations to be evenly spaced in time. So the fundamental difference is, let's say, this is an example of one of these algorithms that fit harmonic models. So we have harmonic functions that are used to segment the time series, so to find homogeneous sequences in time in terms of spectral conditions. So the time series can be irregular, and these models try to fit these harmonic functions. While if we use, let's say, a fixed number of observations per year, in this case is one observation per year, we get more linear patterns. So we usually fit linear models for modeling the changes, the changes throughout time. The main goal of this work was to develop a framework for the detection of no-standard replacing disturbances. Let's say disturbances in general, but we focus on no-standard replaces ones that are usually challenging to detect because of their low magnitude. So the research was carried on in Sweden, and we used the subannual time series from Sentinel-2. So we had some specific objectives that were like to minimize the intra-annual seasonality, to improve the sensitivity of the landing algorithm to detect the subtle changes. And also we wanted to evaluate the different composite strategies and spectral indices for the detection of these no-standard replacing events. So we first compiled a disturbance dataset using different sources from the National Forest Inventory that provided us with the plot level information about forest damages. And then we had data from the bark beetle study areas, either at the plot level or at the tree level. Then we used the harvested data related to, at the patch level, related to thinning operations. And then we also used a forest fire data set that comprised all the polygons from recent wildfires that occurred in Sweden. For the harmonization of this different data set, we basically converted all the information at the plot level and the tree level to the polygon level. So for this, we used a semi-automatic visual interpretation of aerial orthophotos in combination with the analysis of Sentinel-2 time series in like visual on-screen interpretation of the Sentinel-2 time series. And for developing the patches, the disturbed patches, we used these AI-assisted segmentation models that allowed us basically to find disturbed patches that were close, for instance, to an NFI plot where some disturbance was recorded. So we looked at the orthophoto that was acquired closer in time to the time of the survey of the NFI plot, and then we looked for the surroundings of the NFI plot to look for some patches that were compatible with the type of disturbance that was recorded in the plot. And then we did visual interpretation and then this delineation of the polygons with this AI tool. Here is not visible, but we ended up with polygons around these NFI plots. So we basically created polygons that were compatible, as I said, with the disturbance that was recorded in the NFI plot at the time of the survey. So then once we created the disturbance data set, the reference data set, we did some modifications to this algorithm that was originally developed for the analysis of Landsat time series on an annual basis. So this algorithm is meant for the analysis of 5-dimensional time series that include information from the spectral, from the temporal, the spatial, and the spectral domains, It works considering a spatial neighbors and a spatial neighborhood. We use a 3x3 spatial kernel, and this analysis then includes different spectral bands and indices and the information from the surrounding pixels, but the final output is on a pixel basis. So what we changed in this new version of the algorithm was the way with which the time series across this panel of time series were aggregated to find the different changes. So we use this L2 norm to aggregate the deviations from linearity in the model. That is basically enhance the sensitivity of the algorithm to dense changes. For dense changes, I mean when we have changes that are common among pixels and spectral indices or spectral band. So if at a given time we have a common change, the algorithm is able to detect that change, and this type of modification enforces this detection. Then we modified how the algorithm estimates the variability, the standard deviation within the time series, and then we also updated the noise filter to be robust against outliers. The code is written in C++ and is wrapped up in an R package. So for the testing and the validation, we used 8 test tiles of 60 by 60 kilometers that were spread from the south to the north of Sweden, and they comprised a variable number of polygons depending on the availability of data, of the disturbance data from the reference data set. In the south, we have quite many validation points because of the availability of thinning polygons from harvester operations. And we then developed this validation scheme based on the inner stratum, the disturbed stratum, and outer stratum that is bordering as a positive buffer bordering the disturbed patches. So with this approach, we ended up with around 10,000 validation points within the inner stratum and the outer stratum. So for limiting the variability within the years, we developed a seasonality normalization approach that is basically the rationale behind this is that we want to limit the changes that are occurring within the season, within the growing season, because we are considering the data acquired between June to September of each year. So we have a sub-annual time series, but our data comes only from the vegetative season. And we want to limit the variability that is within the growing season. So we basically computed an image composite, so a cloud-free image composite per month. So one in June, one in July, in August and September. And to limit the differences that are related to this, that are related not to the changes caused by disturbances, but those related to seasonality, we integrated during the compositing phase this normalization approach that has been tested with multidimensional medians that are these midoid and geometric median that are two popular algorithms to generate cloud-free image composites. So we developed basically this weighting scheme that is based on spectral distance measures, namely the Euclidean distance and the spectral angle mapper. So we basically found a reference value for each year, and then we weighted all the observations that were available throughout that year with these spectral distances from the reference. This allowed us to reduce the intra-annual variability due to seasonality. And then we used some sigmoid functions to normalize these spectral measure distances, spectral distance measures within each compositing window. As I said, the compositing windows correspond to single months. Moving to the results, when we applied the seasonality normalization using either the medoid or the geometric median, we observed a reduction in the seasonality patterns around 40%. So what we are seeing by using some statistical tests for evaluating the presence of seasonality patterns was that most of the seasonality was associated with spectral bands in the SWIR region, in the SWIR wavelengths, so as also for spectral indices that are based on SWIR bands. Overall, after this normalization, most of the spectral indices and bands displayed a seasonality pattern like the proportion of the time series that displayed a significant seasonality pattern were around 10 to 13%. So there is a quite big reduction in the seasonality pattern. That is what we were aiming for. And yeah, here I will show some of the results related to bark beetles. Here we have these results that are related to the spectral magnitude, so the spectral differences that were measured by using this the change detection algorithm. And we had reference data from this natural reserve in the southeast of Sweden that was heavily attacked by bark beetles in 2020, 2021. We have, let's say, we have reference data for 2020 and 2021, but the attacks started before in 2019. So here you can see these are manually interpreted single trees that were video interpreted from drone images, from images acquired in 2020. So there is a fairly good correspondence between the patches that were detected using with the Sentinel-2 based algorithm and the trees that were attacked in 2020. So you also see the intensities. So the trees were basically there were clusters of trees attacked, and here, and you can see this the density of the trees is also quite matching these patches. And then, for instance, for 2022, we also had this video interpretation of the attack trees from multispectral imagery from drones, and also the patches that were detected with Sentinel-2 were quite correspondent with the single trees detected from drone imagery. Another example, this is from Remninstorp, and here you see some example of this segmentation using different vegetation indices. As I said, these vegetation indices are analyzed concurrently, so the algorithm finds some common change points and then summarizes the change points across the vegetation indices. So this is an example of a change in a pixel and in a surroundings of a plot that was surveyed in 2019. So the algorithm detected the change at the first observation of 2019. And then there was also a detection of a subsequent disturbance in 2020 that is related to the salvage logging that was performed afterwards. And like similarly, here we have this patch where trees, where some disturbance was detected in 2018 and then in 2019. So if we look at the image in 2020, here there are patches of trees that were actually dying. So they started, the dieback started in 2008 and then continued also in 2019. And here you see the salvage logging in 2020 that was recorded as a subsequent disturbance in 2020 after the beetle attack. So when we basically compare the different compositing algorithms, we found out that this weighted geometric median achieved the best results with the FON score around 75%, 0.75, and these results are considering the disturbances that were detected in the same year. But if we apply a 1-year offset, we see that the amount of disturbances of events that were correctly identified increased. So we get an increased F1 score of 0.8. And so this was, let's say, the weighted geometric median with the phenology normalization achieved the best results. And when we look into the results, we compare the results among different disturbance agents. We see that the performances are similar, and we have good performance in terms of detection accuracy for beetle attacks. And let's say this data set, as I said before, is dominated by thinning operations. So I would say that this is the most robust, like the accuracy results related to thinnings are the most robust and impactful in this type of assessment that we did. But here again, applying a 1-year offset causes an increase, determines an increase in the detection accuracy, because basically this increase is related to the detection of those disturbances that occurred after the growing season, when we don't have data until the next year, the growing season of the next year. So to wrap up, we've seen that the modeling Sentinel-2 time series with the linear trends is a useful and effective way to the detection of nostalgic effects in disturbances. Although the limitation related to the availability of data to the vegetative season causes lags in the detection. But this is what we were expecting from optical data that is limited by cloud cover and snow cover. We are we are finishing this sensitivity analysis to find which is the best combination in terms of Sentinel-2 spectral indices, in terms of number, and which spectral indices are performing best for the detection of these disturbances. And we are also working on this on the production of wall-to-wall maps, disturbance maps, using high performance, the computing resources from a high performance cluster that is provided by the Umeå University and close to SLU. And the next steps will be to classify each disturbance patch into its agent. So we want to attribute not only know when the change, the disturbance occurred, and which was the severity of the disturbance, but we also want to know which was the agent that caused that disturbance. And